Hello, Azizul, are you there?
Yeah, yeah.
Okay, okay. So we can start. Okay.
So, yeah.
So
So,
good evening to all, and so today's we have Dr. Azizul Hoque. Azizul completed his MSc in mathematics from Gauhati University in 2008. Then he has completed his PhD in 2015 from the same university, Gauhati University. After that, he has joined as a postdoc at Harishchandra Research Institute of Allahabad, where at the same time also I was also the postdoc. So now he is working as an assistant professor at the Department of Mathematics in Rangapara College, Sonepur, Assam. His main area of research is number theory. Mostly he's doing works on Diophantine equations and quadratic fields, binary quadratic forms, class field theory. All this he has many publications also till now. So on today he will going to present a correspondence between binary quadratic forms and quadratic fields. So I request Dr. Azizul to deliver the talk. Thank you.
thank you so much. So, is it visible?
Yes, yes, yes.
Okay. So, good evening to all. So, first of all, I would like to thank Dr. Sudhanshu Shekhar Rawat and the other host. So, basically, in this talk, I would like to make a connection between this the class number of binary quadratic forms and that of real quadratic quadratic forms, which is well established, and I will be using that one to uh, discuss some problems in the divisibility of the class numbers of real imaginary quadratic forms. So I'll be using the divisibility of the class numbers of binary quadratic forms to discuss that of the imaginary quadratic forms. Okay. So hopefully uh, after the talk, some of the students will take up some of the problems from here out of this talk. So basically, I will okay. So in the first half, I will discuss some basic uh, ideas or the motivations or the problems, and then I will discuss the main correspondence and followed by the applications of the same. Yeah. So while we try to describe the arithmetic objects, it is often helpful to know how to write down those objects and and especially to parameterize those objects. So one of the good way is to do the parameterization is to analyze the orbit of these algebraic groups. An example of algebraic group representation that is studied by Gauss in his Discussionis Arithmetica in 1801, that is binary quadratic forms. Basically, this binary quadratic form is a lattice that is, yeah. So the set of all binary quadratic forms that forms a lattice. In fact, set of all binary quadratic forms over integers that forms a lattice in the two-dimensional representation of SL2Z. Okay, so this is the basic. This is the standard form of this binary quadratic form. So ax square plus bxy plus cy square, this a, b, and c, these are integers, and thus the term is known as this integral binary quadratic forms. So we have you can similarly one can consider this n-ary quadratic forms or high degree quadratic forms. So here, this A, B, C, basically we consider this this A, B, C to be co-prime. Otherwise, you can make it, you can convert it into that form. And those type of forms are known as primitive binary quadratic forms. And now see, if we fix this A, B, and C, and if we allow this x, y to be integers, then basically this will give us integer values. So in fact, an integer m that is represented by this f. So let us take an integer m that will be represented by f if we can find out some integers that such that the value of this form at those 2 points or at for those 2 points is equal to m. That means this m can be considered as the value of this binary quadratic form and for these two values. Basically, we are talking about the solutions of this equation. So f of xm ym is equal to m, or you can say that just this equate this with some integer, say m. Then basically we talk about the existence of solutions of that equation in integers. Okay, so if these integers are, if the solutions are relatively prime, then we say that such a representation is proper. Otherwise, it is improper. So basically, we will be dealing with these primitive binary quadratic forms. Of course, this is integral and this proper representation. Okay, so one of the earliest
Sir,
example of, yeah.
sir, can I ask a little question? Sir, what is sir
Yes, sure.
integral binary quadratic form, sir? What is what is its definition, sir? Can you please
Okay.
tell me?
So if you allow these coefficients, this a, b, and c,
Sir.
okay. So if
Yes, sir.
a, b, c, these are integers, then we say that it is integral binary quadratic forms. Okay.
Okay. Okay.
So if you allow this a, b, c to be real, then you can say that it is over the real. Okay.
Okay. Oh, okay, sir. Okay, sir.
So it is integral because of this a, b, c. These are integers.
Okay, sir.
Okay. So one of the earliest example of binary quadratic form is this one, x square minus ny square. So x square minus ny square. Basically, this was studied by the Pythagoreans and the Indian mathematician this Brahmagupta. And basically, they were trying to find out the approximate value of some square. Say, if n is equal to 2, then that was studied by Pythagoreans to find out the approximate value of root over 2. And similar problems were considered by Brahmagupta. So nowadays, this if we equate with 1, then this type of equations are known as Pell's equation. And basically, this gives the representations of this minus this gives the representation of this 1. So for each value of x and y, this will give you a representation of this 1. So another form was considered by Pharma in 1640. That is this one, this x square plus and y square. This n is a positive integer, and in fact there is a nice book on this structure. So one can go through this book that is written by David A. Cox, and there's a nice connection also with Pharma, some of the Pharma's theorem and class field theory as well as the complex multiplications. So this is a nice book. So the beginning of these quadratic forms, or say integral binary quadratic forms, that was developed by Lagrange and Legendre, but the modern form was given by the Gauss. So here the basic questions is these are the basic questions that which integers can be represented by a given quadratic forms. So suppose we have a quadratic form, then that quadratic form, okay, what type of integers can be represented by this quadratic form? So basically this question is can be looked into another way, can be looked in other way. What is that? If I equate this is equal to say m, the question is that is there any integer solution of this differential equation? Say, okay. So if I start with this binary quadratic form by fixing a, b, and c, and equate that to some m, the question is that whether this equation has integer solution or not. Now, if that equation has some integer solutions, the next question is that how many solutions are there? Okay, so basically that means that in how many ways can a given integer be represented by a quadratic form? So these are the basic questions that usually studied in this topic. Okay, so let us use this notation. F is equal to this one. This means ax square plus bxy plus cy square, basically this one. So I'm writing this f is equal to this. It means that this is the this binary quadratic forms. Now the discriminant of this is given by this b square minus 4ac. Okay, and this binary quadratic forms is called independent if it represents both positive as well as negative integers. In other words, it is indefinite. It is indefinite if the discriminant is positive. So if the discriminant is positive, in that case, this represents both positive as well as negative integers. So that is why the form is called indefinite. So otherwise it is definite. It is definite means so definite means this form represents only positive integers or only negative integers, and in that case the discriminant is negative. So if the discriminant is negative, then it is either positive definite or negative definite. So positive definite means it represents only positive integers, and negative definite means it represents negative integers. Now suppose I have given a positive definite binary quadratic forms, then if I multiply that forms by say -1, then I will get the negative definite integral form, by integral binary quadratic form. Okay, so another thing is that, see, this A may be even or may be odd. So if A, sorry, if B may be even, may be odd. So if B is even, then this is congruent to 0 mod 4. And if B is odd, then this is congruent to 1 mod 4. So what does it mean? It means that the discriminant is always 0 or 1 mod 4. Okay, so is there any question here?
Any questions
Okay,
from?
so
Okay, you proceed.
Yes, sir. One question.
Okay,
yeah,
Aditas, you can ask. Okay.
So how do we conclude this? Like if that is positive, then it will give only positive definite.
okay. So so make it. This is the given quadratic form. Now make it complete square. Okay. So if you make this one is complete square, then you will get something square minus delta this one into y square will be there, and from that you can conclude that one. Okay. So make this one as you can convert this into some square into delta something square. Okay, so from that you can conclude whether it is indefinite or definite. Okay.
Okay, sir.
Okay. Okay. So now let us look at this diagram. So can you guess this? What does this represent, or what kind of binary quadratic form this represented by this one? So let us guess this one. So what is the coordinate of this point? This point is 0 comma 3, right? And so 0 comma 3 here, and this is sorry, 3 comma 0, and this is 0 comma 3, and this one is 3 minus 3. So I have this 9 points. Sorry, 6 points are there. So something corresponds to these points. There is there is a binary quadratic form, and see, if I consider this something, say ax square plus bx square plus cy square, and then if I put this point over there, then you'll get something, and from there you can find out that this is the exact binary quadratic form, and corresponds to this one. If you put it here, x is equal to 3, so this is here you'll get 3 square 9. This will be 0, this will be 0. So basically this represents this 9. So similarly each point this one. So here how many represents are there? 1 2 3 4 5 6. Okay, so there are 6 representations of 9 with the help of this binary quadratic form. Okay, so with the help of this one, you can represent this 9 in 6 ways. So similarly, we have another example, this one. Okay. Okay, so next, okay, so suppose we have given a binary quadratic form. Is it possible to construct another binary quadratic form with the help of the given one? The answer is yes. So suppose this one is given. So what is that? This f is equal to this one. This means that ax square plus bxy plus cy square. Now, if I allow these linear changes in the variables, say x linear change, x linear combination or y linear combination. So what I mean that f of x y is equal to this one. That means ax square plus bxy plus cy square. Now if I change that x by say ax plus b, say says uh, this rx plus sy. Similarly, replace that y by say tx plus uy, then you will get another binary quadratic form, and that is basically means that for any element sigma of this SL to Z, define this sigma f. Look at the action of the sigma on f that is defined by this one. So sigma, this is a binary quadratic form. The sigma act on this like this one, those f of this one. So this is a matrix, 2 by 2 matrix. So if I multiply this one with this one, you will get just like that, Rx plus Sy and Ux plus By like that. So you're getting another binary quadratic form. So what does it mean? It means that this SL to Z that acts on the set of binary quadratic forms. But the interesting fact is that it preserves one thing. What is that? That is discriminant. That means the discriminant of this form and these forms are the same. And this gives us a, okay, so this form and these forms are equivalent to each other, and this equivalent relation and this gives us a equivalence relation on the set of binary forms. Thus we can talk about the classes of these binary forms, binary quadratic forms. And basically the collection of these classes of binary quadratic forms that gives us a natural group structure. Okay, and that structure was given by Gauss, and that was the best discovery of at that time, because at that time the present structure of group at that time the group theory was not does not existed at that time. Yeah, so that is why this discovery was the best of one during the time. Okay, so next thing is that if I take two binary quadratic forms, those are equivalent, and thus okay, those are equivalent and the discriminant are identical. Since the discriminant are identical, so this acts, this restrict this positive definite to positive definite and negative to negative. So it converts negative to negative, positive to negative, indefinite to indefinite, as well as, so thus you can say that two sets, two equivalent binary quadratic forms that represents the same kind of integers. Okay, so suppose f represents say m1 and m2, then this sigma f will represent the same set m1 and m2. Okay, so that means in an equivalence class that represents the same kind of integers. Okay, so basically this the number of classes or the cardinality of that group is called the form class number. Nowadays it is known as narrow class number of the given discriminant. Okay, now the above question to determine which numbers are represented by a given binary quadratic form, one can study any binary quadratic form in the same equivalence class. So from a class of binary quadratic forms, just it is sufficient to study a single binary quadratic form to answer this question. Okay, so but there is no theory to determine which are these, but there is a criteria to identify those numbers. So what is that? That says that an integer n is properly represented by some binary quadratic form of discriminant say d if this d is a square mod for n. So if d is a square mod for n, then that n can be represented by some binary quadratic form of this given discriminant. Okay. So now the next question is that how to find out these classes of equivalence classes of these binary forms or the form class number. So how to find out those forms? Okay, so one way is to do it like this, is through using this primitive positive. Okay, using this reduction. What is that? If it is positive definite, then in that case, that form will be reduced form if this happens. This modulus of B is less than or equal to A or less than or equal to C. And in case B is positive, then one of this equality becomes one of this inequality becomes equality. So on the other hand, for indefinite forms, it is reduced if this happens. So this absolute value of 2 absolute value of A minus root over D is less than B less than this root over D. So if a form that satisfies these conditions, then we say that it is reduced. Okay. Now it is well known that so one can prove that these reduced forms, the number of reduced form with a fixed discriminant say D is finite. Okay, so the number of reduced form with a fixed discriminant is finite. So the number of reduced form is finite. And another theorem that says that in case of imaginary quadratic, in case of positive definite, in case of positive definite, each class contains only one reduced form. Each class contained only one reduced form. And since the number of reduced form is finite, so you can say that the number of classes is also finite. What does it mean? It means that the form class number is finite. Okay, so similarly, in case of indefinite form, again, one can conclude that the form class number is finite. But in this case, there is some problem. The problem is that in case of positive definite form, each class contains only one reduced form, but in this case, it may each class may contain more than one reduced form. Okay, so that is why to know the exact number of these equivalence classes, one need to find out the equivalency rate among those reduced forms. Okay. Okay. So is there any question? So I'll be moving towards the other part.
Yes, sir. So one
Yeah,
question.
yeah, sure.
What is meant by the D is a square mod 4n?
D is a
Uh, in point number 4, so D is a square mod 4n. So what is meant by that?
okay. This one. So this means that this D is a quadratic residue of this one. Okay. So D is congruence to something square mod 4. Okay. So D is congruence to say A square modulo 4n.
Okay, okay, yes.
Okay. Okay. So this is the part about this binary quadratic forms. Okay. So let us move towards the other part. These quadratic fields, number field. So a number field is a finite extension of Q. What does it mean? It means that this K is a finite dimensional vector space over this field. That means this K has a finite dimension, finite basis over this Q. So, okay. So this K is a finite dimensional vector space over this Q. It means that it has a finite basis. So now, if the degree of this over this Q is equal to 2, then we say that it is a quadratic field. Okay. So it means that if we consider this K is a vector space over this Q of dimension 2, that means its basis has only 2 elements, then we say that it is a quadratic field. Okay. So now, what is an algebraic integer? It is just a complex number that is a root of some monic polynomial in G. Okay. It is just a root of a monic polynomial over the integers. Consider a monic polynomial, take a root that is a complex number, that is an algebraic integer. Okay, and there is a nice structure among this on this algebraic integers. That means the set of all algebraic integers in a number field, say K, it forms a ring, which you call the ring of integers. And thus we have this kind of a structure, this Q, take an extension, say K, and similarly, here the integers are this one, and we have this extension, this ring extension is there, and this contains this. For example, if we consider K is equal to this imaginary quadratic field, because imaginary because this is minus, okay, so minus 5 is there. Okay, so what are the types of the elements here? This A plus B root over this minus 5. With A and B are rational numbers, and the integers, it is just take the coefficients from the G. So what is the ring of integers? It is so it depends on this integer. So minus 5. So minus 5 is congruous to 1 modulo 4. So it remains the same. So the general form of this quadratic field is Q root over say D. If D, that Q root over D, if D is positive, then we say that it is real quadratic field, and if D is negative, then we say that it is imaginary quadratic field. And if D is congruous to 1 mod 4, then in case of 1 modulo 4, then the discriminant is D itself, and if D is congruous to 2 3 mod 4, then it is its discriminant is 4D. And similarly, we have a theorem to characterize the ring of integers. So in this case, the ring of integers is this one. Okay, so thus we have this structure just like this one. This is just an example. Okay, so let us draw a remark here about the structure of the integers here and then here. Okay. So in case of this G, the set of all rational integers, we have a nice property. What is that? That is called unique factorization of integers. So that means every composite number can be expressed as a product of primes. Okay, but this does not happen in case of ring of algebraic integers. So here we have nice property that unique factorization of, but here we don't have that factorization. So to study this failure that happens in this one but not this one, so to study this failure, the theory of these class groups has come up. Okay, so basically, look at this example. So I'm considering the same example, same field, k is equal to this one, here this one. So if I look at just this one, so here this 6 has a unique representation, that is 2 into 3. But if I allow in this ring, then we have one more representation. That means 2 representations are there. Okay, so in this case, we have the class number of this k is 2. Okay, so to discuss this type of failure, we have this class group. So what is that class group? So to define that class group, we need another concept, so-called fractional ideals. So start with the number field k. Look at a submodule over this k. Over the ring of integers, say I, such that this for some non-zero algebraic integers, this pushes inside the ring of algebraic integers. So this I may not be inside this OK, but if I multiply this by some algebraic integer, then it pushes inside the ring. For example, if I consider simply say Z, the ring of rational integers, and consider the all half integers I mean half, then 3 by 2 and so on, that does not contain do not contain inside that Z, but if I multiply that by 2, then it pushes inside that Z, it becomes the integers. Okay, so half integers, that is a fractional ideals of that Z. So similarly, you can give plenty examples of fractional ideals. And here we have a nice structure. What is that? This fractional ideals gives a group structure. So there is a nice multiplication property, and so you can define that structure, and you can define the group of fractional ideals. And in fact, that gives a abelian group. So we have a nice abelian group here. And on the other hand, if you collect the principal fractional ideals, then you have this nice quotient structure. Okay, so this is an abelian group, and this is a subgroup of this one. So we have this quotient structure, and this quotient structure is known as the ideal class group. So previously we have this a form class group, but here we have this ideal class group, and the cardinality of this group is known as the class number of the field, this is K. Okay, so by the way, this OK is the maximal order. OK is the maximal order in K. You can consider other structure, other order. So if I consider any order, say O, then we have the similar kind of a structure, and those type of groups are called Picard group. So I'll be coming into that. So similar kind of a structure in case of if it is OK, that means the maximal order. In case of maximal order, we have this class group. Otherwise, it is known as Picard group. This type of a structure are called Picard group. Okay. Okay. So here, what are the problems? So, what is the size of this CK? What is the size of the class group, or you can say? Okay, so it is well known that the class number is finite. That means the size of this CK is finite. But the question is that what is the exact size? Suppose I have you have a group class. You have a class a number field. Then is it possible to identify the exact class number? Well, or exact class number. Okay, so I'm giving you q root over say 500. Then what is the class number? You can easily find out. But if d is arbitrary, is it possible to bound to that number, the class number of that one, or the size of this one? Or you can say that at least can we say something about the factors of the size of this CK? Okay. So similarly, another question is that what is the structure of this CK? So since this is an abelian group, this CK is an abelian group. So you can talk about the structure of this one. So for example, how many copies of say z mod c z mod pz will be there for some given prime? Okay, so the next question is that do these questions have a quantitative answer depending on the discriminant of this K? Okay, so suppose the discriminant is given, the question is that how many fields will be there, say up to discriminant say less than or equal to some bound, say x. So up to say x. Okay, so bound the discriminant up to x. The question is that how many fields will be there whose class number say has a factor say n, or it has a copy of z mod pz or z mod nz. So can we bound these two questions? Can we give a bounds on that? Okay. So in case of imaginary quadratic field, this class number can be made as large as possible by allowing this discriminant to be large. Okay, so can we bound this class number? Okay, so it says that the class number can be made as large as possible depending on the discriminant. And in fact, it is till now. Okay, now I think it is it is proved by Heilbronn. And then there is a list of lower class numbers for imaginary quadratic field. So there is a list, say up to say class number 1. There are 9 imaginary quadratic fields. For 2, there are some fixed number of imaginary quadratic fields, and so on. So Gauss give a list of imaginary quadratic fields of class numbers up to 100. And that problem is completely solved by 2004. On the other hand, for real quadratic field, it is not yet known whether there are infinitely many real quadratic fields are there or not. No. Okay, so in fact, there is a conjecture that there are infinitely many real quadratic fields with class number 1. So there is no progress on this conjecture. Okay. So similarly, there is a questions about the structure, that how many copies of Z mod and Z will be there in the class group. Okay. Yeah. So here, suppose n divides the class number. So this means the class number of this of a number field say k. Suppose n divides the class number. What does it mean? It means that the class group, it has a copy of Z mod n Z. What does it mean? It means that the rank is bigger than or equal to 1. So the rank is at least 1. So rank means it is the number of copies of so n rank means it is number of copies of Z mod n Z. So it has at least 1 copy. So the rank is at least 1. Okay, so there is a conjecture, so it is widely believed to be true, that the rank is unbounded when k runs through all the quadratic fields. And in fact, similar kind of conjecture can be posted for any number fields. And this is widely believed to be true. Okay. So now look at this the correspondence. So I start with an integers a d, and d is congruous to 0 or 1 mod 4. That means d is the discriminant of some quadratic form. So I can write down d is equal to say f square into dk. So dk is the square free part of this d. So this dk, this is called the fundamental discriminant, and this f will be the conductor of some order. And I'm considering a quadratic field of discriminant this dk. So with the help of this dk, I'm considering a quadratic field. Say for example, this q root over d is a dk. And OK is a order of conductor this f. Then there is a bisection between this this Picard group of okay, so narrow Picard group of this order, and so this means that the fractional ideals of this one, the group of fractional ideals of this O, quotient it by the group of principal fractional ideals in O with norm positive, with positive norm. Okay, so we have in the numerator, we have the group of all fractional ideals in O, quotient it by the group of principal fractional ideals with positive norm. So that is P plus. And this means the primitive binary, the group of primitive binary quadratic form, and this plus it represents positive definite. So this means the group of or the set of all positive definite primitive binary quadratic forms of discriminant D. The set of all positive definite primitive binary quadratic forms of discriminant D. Okay, so we have a nice correspondence between these two objects, and those maps are given by this one. So these are the explicit form. So I think Sudhanshu.
Yes, yes.
Yeah. So how much time I have?
So it is. So you can, if you want, you can continue. Otherwise, you can also conclude your talk. So there is, because
Okay.
we
So
can go up to 6 o'clock. So
okay.
five more
So
minutes.
okay. So 5 4 minutes. So maybe I will go to directly go to the some problems and yeah.
Mm.
Right.
Yes, yes.
Okay. So so this is the main correspondence, and here uh, I would like to draw some conclusion remarks. So in case of imaginary quadratic field, this peak plus and peak are identical, are the same, because in case of imaginary quadratic field, the elements are the norm of the elements are always positive. So there is no question about this negative norm elements. So that is why we have the group of all fractional ideals quotiented by the group of principal fractional ideals, because here we have only uh, elements with positive norm. So there is no question about this negativity. Okay, negative norm element. So thus we have this structure. So, and in case of real quadratic field, this peak O is isomorphic to, so peak O basically this one, this O, JO divided by PO. So JO means the group of all fractional ideals, and this is the group of all principal fractional ideals. Now use the third isomorphism theorem. You can write down this. This is isomorphic to this one, all thing. And this is basically the peak plus, and this means this one. So this means it contains the elements, the ideals with positive norm as well as negative norm, but here we have only positive norm. So the index of this one is the order of this one is at most 2. Okay, so the order of this is less than or equal to 2. Now in case of this OS star, that means in case of this non-zero elements of this O has an element okay, in case this O has a non-zero element of norm -1, in that case you can make a connection between this positive norm ideal as well as the negative norm ideal. So there is a connection, you can make that connections, and so in that case this will be 1. If this is 1, then you will get the number of elements here is equal to the number of elements here. Otherwise you will get this one. Okay, so we have so in case of this D is positive, in that case we have this one, because in case of binary quadratic forms with positive discriminant, that means we have this indefinite structure, indefinite binary quadratic form. So in that case there is no question about this positive or negative positive definite quadratic form. So in that case we have this structure only. So if I sum up this one, then we'll get this. For imaginary quadratic field we'll have this one, and for real quadratic fields we'll have this one. Sorry, so this is a real quadratic field, this is not imaginary one, so sorry for that one. This should be real. Okay, so again, if we want to use this one in my problem, then we need to work with this one to convert into some other form. So I'll be showing that one. So I'm skipping this problem. So the divisibility problem. Okay, so basically here I'm considering this kind of field, q root over q square minus p power n. So here it is far more easy to deal with this kind of imaginary quadratic field, that is q root over q square minus p power n, where q and p both are primes. But if I allow this p to be some other integers, not prime, if I allow this p to be integer, in that case it is quite difficult to handle. So, and that is why I'm trying to use this this correspondence to get this problem to be done. Okay. So basically, so I'm removing this one. So this is a nice generalization here. So I'm allowing here this L to be any integer. So I'm taking here L is equal to congruous to 3 mod 4, but I can allow this L to be any integer. And for that, I'm okay. So I have deduced this one from this concept from this concept. That's for imaginary quadratic field. Okay, so I'm using that one. I use that one. With the help of that one, I have found this S star minus D. What is this? S star minus D. It means that the class number. That means the class number of the binary quadratic form, and this means the class number of the imaginary quadratic form q root over 40, q root over minus d. Okay, so here we have this class number of imaginary quadratic form. Here we have the class number of binary quadratic form as forms. Yeah, and this is the main connections in case of this exact class number. So basically, what we do, we have done here this one. We have converted this problem into some binary forms, and from that forms we have deduced this S star minus D, and from that, with the help of this one, we have to this conclusion. We have proved this result. Okay. Okay. So by this, I'm concluding this one, this talk. So if anyone is interested, then you can go through these slides, and maybe someone can write to me if there is any problem of regarding these theorems or all these things. Yeah. Or if anyone is interested, then he or she can contact me. Yeah. Okay. Thank you. Okay. So by the way, there is some nice problems here. One can take up these problems. It would be better one if anyone is interested, he or she can take the screenshot of these problems. Yeah.
Please hold for a few minutes so that they can.
Yeah.
Excuse me, sir.
Yes.
Yeah.
Yes, sir, I have one question. Like,
Okay.
in the fifth slide, can you go to the fifth slide?
Yes.
Yes, sir. Here you were saying about the number, this integer n is properly represented by this d is a square mod 4n. So what if the integer is prime? Then is there any uniqueness to the this quadratic form?
This one. This one.
No, sir. The previous one. Sorry, the fifth slide. What I'm basically asking is, what if n is a prime number? Then is there anything unique about those quadratic quadratic forms?
Okay, so if n is a prime number, then there is a nice theorem that about the structure of this the discriminant. Okay, so with the help of this legendary symbol, there is a nice theorem. You can go through that theorem. Okay, so if n is any prime, then I think n is if n is a prime, then p is congruous to something 1 modulo 4 or 1 modulo 8 like that. There is nice theorem there. Yeah.
Okay, so is there any name for that theorem, or I can just type on internet directly?
Yeah, so you can directly type into the internet. on the internet to get that information.
Okay, sir. Thank you.
Any other questions?
So you can take this the screenshot of these problems so that you can discuss or you can work with that one.
Okay, so
Sir, can you please again tell me what is a class number, sir? Class number.
Okay, so class number of quadratic fields or number fields.
Quality field, sir. Quality field.
Okay. Okay, so for any number field, so look at the group of all fractional ideals. Okay,
Okay.
all fractional ideals that forms an abelian group,
That forms an
and
available.
abelian group, yeah,
Yes, sir.
and then take the collection of all principal fractional ideals.
Special
Okay,
fractional ideals.
principal
Okay.
fractional ideals, and these principal fractional ideals will be again a group, and in fact the latter one will be a subgroup of the first one. Okay, the group of all principal fractional ideas will be a subgroup of the group of all fractional ideas,
Yes.
and in fact it is a normal subgroup. So we have this quotient structure. That quotient structure is called the class group. Okay, so that quotient structure is called the class group, and now look at the cardinality of that class group. Okay, look at the cardinality of that class group, that is known as the class number.
Okay, sir.
So is there any other question?
Difference between an ideal and a fractional ideal, sir. Difference between ideal and fractional ideal, sir. Can you please tell me?
So you know the definition of ideals, right? So so look at fractional ideals. It has the fractional structure. See, this may not be contained in this ring. Okay. Okay. This I may not contained in OK, but if I multiply these by something, then it becomes a subset of this one. Okay. So that means basically this I has a fractional structure. For
Okay,
example, if
sir.
you consider this Z, okay, the ring of integers, in that case, this 2Z is an ideal, right?
Yes, sir.
But Z by 2, half of Z, it is not an ideal. But if you multiply that half of Z by 2, then it becomes an ideal. That means it contains in that Z. That means 2Z is an ideal.
Yes, sir.
2Z is an ideal, but Z by 2 is not an ideal, but Z by 2 is a fractional ideal.
Okay.
Okay.
so any other questions? So it is a very nice talk, and thank you, Azizul, for giving of your time, valuable time for our students. So let's thanks the speaker once again by clapping, by unmute and clap.
Thank you so much.
Thank you, sir.
So just I would like to just I would like to refer a book on this one. I think it would be good to go through that book. What is that? Yeah. Just wait. There's a nice book. Okay.
So you can send that book to me so that I can share to the all with all the students. It is no problem. There
Yeah,
is no
it is
problem.
here. Yeah, yeah, I think it is here. I got it. I got it. Yeah, yeah. So I think yeah. So this is a nice book on this one as well as some basic number theory.
So you can
So
keep your front page hold. Okay, huh? So that they can. Is it available online? They can download it or.
yeah, they can download down. Okay, so they can steal this one from LibGen.
LibGen, okay. So
Yeah,
there is a site called LibGen. You can
LibGen.
download
Yeah,
from there. So, okay.
or otherwise I can forward it to you.
Okay, so it is better you can send that copy, send a copy of that book to me so that I
Okay,
can
sure.
forward to all. Okay.
Okay.
So
So thank you,
thanks.
Sudhanshu.
Okay, thank you.
See you.